Hello guys, so this is Christiana once again, and I am going to be going over how to determine the structure of a compound using the Proton NMR, infrared, and Mass Spectra. So first let's read the question that we're given here. The question says the molecular formula for an unknown compound is carbon subscript X, hydrogen subscript Y, oxygen. That is subscript 1 if you don't see a subscript there, and the molecular weight is 60. Okay, so it says the data for the proton NMR, infrared, and Mass spectra for this compound as shown below. Use the spectra and analytical information provided to determine the structure for this compound. So the first step that I would take is to look at the mass spectrum and also use the information that was highlighted. So the first thing you want to do is use the template that you were given for the molecular formula to make what is it called, to make a algebraic equation. Okay, so we were given 6 subscript 8 x, h subscript y, and o, right? And we're given that the total molecular weight should be 60. What we know already is that the carbon has a atomic mass unit of 12, and so we're going to put 12x. So that means whatever amount of number of carbons we have, that we should be multiplying by 12, its molecular weight. And hydrogen we know as about atomic mass unit of 1, so that would just be y. And then we know oxygen has a molecular weight of about 16 AMU, so we just put 16, and we're only given that we have 1 oxygen, so that would just be 16. Okay, so we're going to equate that to 60. So you're just going to solve this like regular algebra. You subtract 16 from both sides, you get 44, and that will equal 12x plus y. So how do you really determine how much x you have and how much y you have? Meaning how much carbon you have and how much hydrogen. So you want to understand that when you have a molecular weight that's going to be split between carbon and hydrogen, the carbon is going to take majority of the weight. So what you want to do is divide 44 by 12 first, right? So when you divide 44 by 12, I believe you get about 3 point something. Let me make sure here. 44 divided by 12, 3.66 repeating, or 3.67. So what you want to do is round down to 3. So we say x equal 3, and the reason for that is if you were to round up and say that x equal 4, when you do 12 times 4, that will be 48, and that would be too many for the remaining molecular weight you have to split between carbon and hydrogen. So x equal 3. So let's go ahead and insert that back in the equation. 12 times 3 plus y equals 44, right? 12 times 3 is 36. When you solve for y, right, meaning you subtract 36 from both sides, you should get y equals 8. So now let everything we know, let's plug it back into the molecular formula. So now we know x is 3, so that's C3. We know y is 8, so that is H subscript 8, and then we know oxygen, we were given that it's just 1 oxygen. So this is our molecular formula, and we derive this from the molecular weight and the mass spectrum. Okay, so yeah, right here is our molecular ion or parent peak. They put 59, but I believe the correction up here says 60. So yeah, let's just put that as 60. Okay, so the next thing you want to do is determine your degree of unsaturation measured in index of hydrogen deficiency. It's also referred to as IHD, right? So let me just give a brief overview of what how to use IHD. IHD is used to determine if your if your compound is gonna have a double bond, a ring, or a triple bond. Okay, so the way you determine that is you're going to calculate your expected number of hydrogen. The way you calculate your expected number of hydrogen is you multiply 2 by the number of carbon that you have, in this case 3, and then you add 2 to that, right? So the generic formula for that is 2 times C plus 2, right? So in this case 2 times 3 plus 2, so that will be 8. Okay, and if you look at our actual hydrogen, we do have 8, right? So the way to calculate IHD is you take your expected HEH minus your actual H, and you divide that by 2, right? So let me just point out something here. For your actual H, you need to know that if you have what's it called? If you have nitrogen, that will count as minus 1H. If you have an halogen, that will count as plus 1H, right? So that means whatever H you have, right? Let's say we add like nitrogen in this formula, then we'll have to subtract 1 for each nitrogen from the H. If we add a halogen, then we have to add 1 to the actual number of hydrogen for this equation. So that is just side notes there. So in our case, there is we had that our expected hydrogen was 8, and we have our actual hydrogen was 8 as well. So that means we have a 0 IHD, meaning our compound is fully saturated and it has no double bonds or rings. Really, what I should say is no pi bonds or rings, but let's keep it as that. Let me change that to no pi bonds. So, because our pi bonds is indicative of a double bond or a triple bond. Okay, so we basically got some basic information. So now the next thing you want to consider is your IR spectrum. So for your IR spectrum, what you really need is to look at the axis is the wave number. The wave number is also equal to your frequency, right? So for this case, I hope you guys know for this particular course, we don't analyze the fingerprint region, which is the region below 1500 centimeter inverse. So let me go ahead and shade that region out so that we know not to look there. So let's put fingerprint right here. Okay, so that means anything above 1500 we do analyze. Okay, that is our functional region. So if you look at our functional region, you see a peak at about this peak, right? This peak is it's about 2900 to 3000 centimeter inverse. That is indicative of a sp3ch. What I mean by sp3ch is like an alkane, something that has no pi bonds, which we already discussed. This is very consistent with what we determined in our previous step. So we also have this other peak at about, what does that, that's about I want to say 3400 centimeter inverse. That is indicative of an alcohol because it's also strong. It's strong. What I mean by strong is it's quite a long peak. It's strong and it's broad, right? It kind of, if you look up here, right here, it basically it joins with the sp3ch peak. So that means it's broad. So this is very particular to an OH group. So that means we're going to have an OH group in our compound. Okay, so far we determined from our molecular weight and mass spec that this is our molecular formula. We also determined that we're going to have an OH group and sp3ch group in our compound. So that's what we know so far. Let's go to our proton NMR spectrum. Okay, so our proton NMR spectrum, the information it gives us is that so let's go from so this is upfield, not upfield, and this is downshield. Sorry, I keep saying shield. Downfield. Well, let's go ahead and talk about being shield and not the shield part. This is shielded, and this is deshielded, right? Shielded and deshielded is gonna have to do with how much the proton is experience electron deficiency. So meaning if the hydrogen is close to an electronegative atom, such as oxygen, fluorine, your halogens, or oxygen, it's going to be more electron deficient, right? So it's going to be more deshielded. It's going to have an higher number on the spectrum. Whereas if it's farther away, it's gonna be more shielded. It's gonna be more. It's gonna be able to hold on to its electron more, right? So let's go ahead and analyze this spectrum. So here we see that we have two splits, right? So you call this a doublet, two split doublet, and it gives us integration of 6. So that means we have 6 hydrogens of that type. Okay, so let's move on to this other one. This one right here, we have a single split actually, so that is a singlet. And what else do we know? That is integration of 1 hydrogen. So that means we have 1 hydrogen of that type. Okay, so let's go ahead and also analyze the next one. The next one, we see that we have 1, 2, 3, 4, 5, 6, 7 splits, right? 7 splits. That is a septet, and that is 1H. So one thing you should know, there are patterns to NMR, right? One such pattern is that when you have a doublet and you have a septet, this is indicative of a isopropyl group. So I'm going to put off to the side here that we have possibly an isopropyl group. Okay, let's go ahead and highlight that. So that is when you have a doublet and a septet split in the same spectrum. Okay, so let's go ahead and try to put everything we know together. Okay, so we go back to our IR. We know that we have an OH group, so let's put the OH group first. Sorry about that. So OH, so this is a possible structure. So we know we have an OH group, so I'm gonna put OH there. Okay, so so looking at what we have in the NMR, right? A 6H means we possibly have 2 CH3s. Okay, 1H means that could mean a CH. It can also mean an heteroatom. An heteroatom is when you have atom that other than carbon that's connected to a proton for the proton NMR. Okay, so the same thing for this, for the 1H, it could be a CH or heteroatom. So we also know that we have an isopropyl group. So how do you think we can arrange this? Well, this is where the up shield and down shield comes into play. So we know our most shielded is this right here, the two CH3s. So we're gonna draw them as far away as possible from we're gonna put them as far away as possible from the OH. Okay, so that would be like CH3, CH3. Okay, so right here we have something that seems to be a CH or heteroatom. And also right here, since there's only one H, that means we could have a CH or heteroatom for that. So how do we determine which one it is? So you see, one is a singlet and one is a septet. Okay. A singlet is usually going to be your OH group, your heteroatom group, because heteroatoms have a different set of rules where they basically can't be split by another, like an adjacent proton. So they're going to have n equals 0, and if that will mean that they're a singlet, right? So that means that OH is going to be about that, and then we're going to have a CH group. So remember, we also said we had an isopropyl group. So let's go ahead and see how that will come to play. Okay, so let's say we draw an isopropyl group right under that OH. Let's see if this follows everything that we've determined, right? So that means we, if you look here, you have a carbon here, a carbon here, a carbon here, right? That is 3 carbons. So yes, in our molecular formula, we do have 3 carbons. And oh, I'm so sorry, that just erased everything. Let me decrease the size of the eraser. Okay, so if we also look, it says that we should have 1 oxygen. We do have 1 oxygen. And hydrogen, instead of you counting individual ones, we determine that through our IHD, right? So we have no missing hydrogen. But if you want to count for certainty, you have 1 hydrogen here, you have 1 hydrogen that's coming off of that CH group, and then you have 3 hydrogen H. So that's 6. 3 plus 3, 6, 7, and 8. So yeah, so everything, it looks good so far. So now let's look if this compound follows this this NMR. Oh, sorry. Yeah, this proton NMR. Let's see. So if we look at this OH group, right, it's gonna have a signal, right? First of all, let's determine how many signals we'll get, right, from this compound that we proposed. This compound that we proposed is going to have a signal from the OH, is going to have a signal from the CH, right, because they're different groups, and it's going to have just 1 signal from this from 1 CH3, because they're basically, the CH3s are equivalent, right? Because they're the equal distance from the OH, and they are both CH3. They're connected this in the same way, so they're equivalent protons. So basically, what you have here is 3 signals. So check, we do have 3 signals. So the next thing you want to check for is that for this OH, we know it's going to be a singlet because it's a heteroatom that's attached to a proton, right? And we know that there's only 1 hydrogen of that type. Okay, So let's look at this one right here. So that's going to be it's adjacent to this CH3 and this CH3. So that's gonna make it so it's, and the reason why I'm not counting this OH is because hetero atoms don't split the adjacent atoms. So if you're counting this and this that are adjacent to it, that means it's adjacent to 6 protons in total. And if you add one, because we follow that n+1 rule to determine how many splits it will have. So with the n+1 rule, that means being adjacent to 6 protons, that means it's going to have 6 plus 1, which is 7. That's a septet, right? And there's only one proton of that type. Okay, so now let's look at the CH3. So because we're only going to be looking at one, it's only going to for both of these CH3, we're only going to get one signal because they are the same connectivity. So they are adjacent to just one proton from this CH group in orange, right? So that's gonna, so we're gonna also follow that n+1 group, n+1 rule, sorry. So that would be that one from the CH, and then +1, that would be a doublet, right? And how many protons of that type do we have? We have 6, because those are 2 CH3s. So if you compare this information to the information that the NMR gives us, you will see that this compound does in fact follow follow the NMR, and also follows our IR, because we have a OH group. And yeah, so this is actually our compound that we're looking for. This is a isopropanol. So let me go ahead and draw it somewhere where it is clearer. So that is our isopropanol. Let us go ahead and put that in orange. So yes, so that is how you determine a compound from a proton NMR, infrared and mass spectra. Let me know if you have any other questions. Thank you so much for watching. I hope you have a wonderful day.